So for this example, I want to look at forces when you could have to combine forces to find the net force on an object. When we go into module 3, there's going to be a lot with net force because you're going to be combining electric forces coming from all sorts of different directions on a single charge. So to start with, I want to review the idea of a free body diagram. A free body diagram is when you draw a picture of the object and then you draw all the forces acting on it. So let's imagine that we have three forces acting on this object. I'll call this one F1 and this one F2 and this one F3. And let's say F1 is 5 newtons at an angle of 15 degrees. And I'm not putting compass directions on this one on purpose because when we look at charges, things like electrons and protons don't carry compasses. And so it doesn't make sense to talk in terms of north, south, east, and west. Instead, it just sort of makes sense to draw the picture as we're working through and use the picture. F2, let's call that 7 newtons. And that one we can see from the picture that I've drawn is just directly to the east or directly right. And F3, I'm going to call 4 newtons, and I'm going to have that as an angle of 25 degrees below the horizontal. Below the horizontal means, like, in this case, it looks like south of east. And then the net force is a vector, which means it's the vector sum of those three forces. So it's F1 plus F2 plus F3 added together, but I've drawn little vector arrows on top of those to indicate that this isn't a normal sum, it's a vector sum, which means you need to add the x components, add the y components, and then combine them separately and put the whole thing back together again in the end. In other words, you're going to find F net in the x direction by adding F1x plus F2x plus F3x, and you're going to find F net in the y direction by adding F1y plus F2y plus F3y, and then the total F net has a magnitude equal to the x component squared plus the y component squared. And the angle is inverse tan of the y component over the x component. So, a couple warnings before we go too much further with this. The first warning is make sure you are in degrees mode. On your calculator, before you do any vector addition calculations, if you're switching between a math class and physics, you're probably going to be switching between radians and degrees. And so you should always double check that you're in degrees mode. And if you don't, if you start getting funny answers, the first thing you should be checking is if you're in degrees mode or radians mode, because it's a common thing to have come up. In fact, I had a student once submit an entire unit test in radians mode and didn't realize it. If you're in radians mode, you're going to get really tiny angles, and that's usually an indication that that's the wrong mode. The second warning is pay attention to negatives. Both when you're doing your calculations, because a lot of people drop their negatives when they're calculating, but also the TI calculators are really a little bit frustrating. Let's say I have a value like x equals -2, and I go in my TI calculator and I try to square that. So I enter like -2 squared, your calculator is going to tell you that's -4. And we obviously know it's not -4 because a negative squared is a positive number. The TI calculators don't put brackets on the squaring. It treats the negative like it's a separate thing. So your TI calculator sees this when what we want it to see is the negative included, which gets rid of the sign. And so when you go to enter negative numbers into your TI calculator and square them, you really need to make sure that you enter them with brackets around them, or enter them without the negative sign and just ignore the negative, because you want that negative squared to become a positive, because that's what we know negatives do. Okay, I'm going to erase some of this so I can start this vector addition. In general, I'm usually going to give you the angle that's between the x-axis and the vector. So for example, if this is my xy coordinate system, and this is F1, which is 5 newtons long and 15 degrees, I'm usually going to be nice and I'm going to give you the angle between the x-axis and that magnitude component, or the x-axis and the arrow. And the reason why that's nice is because as long as that's the angle you're given, you don't have to think too hard about which trig function to use for which component. The x component will always be a cosine, and the y component will always be a sine, as long as the angle you have is the one between the horizontal and the vector. So in general, the components of a vector, so let's say f1 x, which is the x component of f1, is f1 cos of the angle, and f1y is f1 sine of the angle. So we have f1 x component is equal to 5 cos 15, and f1 y is equal to 5 sine 15. And I'm going to encourage you to just leave it written like this. Don't turn it into a massive decimal number just yet. It's so much easier to write it like this and then plug it into your calculator later when you have all the values ready to go. We have now the x and y component of f1. Now let's do the same for f2. So f2, we can see that it's just pointing to the right. We would say that it has no y component, or you could also say that it has an angle of 0 degrees. And then cosine of 0 is 1, and sine of 0 is 0, so it actually works out. But let's just say that f2x is 7 newtons, and f2y is 0 newtons, because we can see that just by looking at the picture. F3, we can see, is below the horizontal, so its y component is down or negative, and its x component is to the right, so its x component is still positive. So f3x is positive 4 cos 25, and f3y is negative 4 cos 25. And then I'm going to find my x and y total. So my f net x is going to be f1x. Actually, I want to grab that one. And f2x and f3x added together. And these are all positive because they're all pointing to the right in the x direction. So we've got 5 cos 15 plus 7 plus 4 cos 25. And now that you've written it out like that, it is time to enter it into your calculator. And I'm just going to go ahead and enter it into my calculator. And feel free to enter it into yours as well to make sure you get the same result as me. So I've got 5 times cos 15 plus 7 plus 4 times cos 25. And that gives me 15.45486 newtons. And we can see that it's positive. We can even see by looking at it that the whole thing is going to be dragged to the right. But I'm just going to make a note of that too next to it. So that way, when I go to find my net force, I'm keeping track of the directions. Next, I want to do my y direction. So F net y. And that's going to be F1y plus F2y plus F3y. Or 5 sine 15, and that's coming from F1, which is directed upwards, so that's a positive y component, and 0, because F2 isn't pointing in the y direction, minus 4 cos 25, and that minus sign is because we can see that F3 is pointing downwards. So it's subtracting from the upwardsness of F1. And then entering that into my calculator, making sure I don't lose that negative sign, I go 5 times sine 15 minus 4 times cos 25. And I have a net force of 2.331136 newtons. And I can see that that's negative, which means it's a downward force. The total F net is those two components squared and added together, then square rooted. I see I have a question coming. For F net Y, oh, did I write cos? No, that was me just being wrong. Did I type it in? Yeah, I did. Whoops, thank you for catching that. That should be a sine as well, which means I'm probably wrong in my answer. Let's try that again. 5 times sine 15 minus 4 times sine 25. Well, at least it's still negative. Negative 0.396778. Thanks for catching that. Newtons, it's negative, which means it's down. Now that I have those two, I'm going to add them together to get the net force. So the magnitude of the net force, and you'll notice I put it in absolute value signs because the magnitude is not the full vector, it's just the number apart. And so I put the absolute value signs around that to say I know that this isn't the full vector, this is just the magnitude. And I sort of do that also as a reminder to myself that I need to remember to get the angle. A lot of times on tests, students forget to get the angle because they've done all of this work and it's just kind of overwhelming, and then they lose track of what they need to do. So it's really important to sort of remind yourself of that. That's part of why I use the magnitude sign. And so that is going to be the vector sum of those added together. So 15.45486 squared plus, and here's the point where on your calculator you need to make sure if you square the negative, you put it in brackets, because your calculator, or at least the TI calculators, don't square the negative when they should. And then going into my calculator, I'm going to grab this one and square it, making sure it's a positive answer, plus the x value, there it is, 15.4548 squared, square rooted, and I get 15.45, which I'm going to just use 2 sig digs. So that's 15 newtons when I round it to 2 sig digs. So that's the number part. I probably should have rounded it to 1 sig dig, so it would be like 2 times 10 to the 2 if I was actually going by the sig dig rules. But I think I'm just going to leave it as a whole number, not quite following the rules because rounding 15 to 20 kind of bothers me. My angle comes from the inverse tan of my y component, which is 0.396778, divided by my x component, which is 15.45486. And you'll notice that I didn't put the negative sign in, and that's because I don't want to confuse it. If I put the negative sign in, sometimes the tan function will give me like 360 minus the value. And I just want to get the value between 0 and 90, and then I'll call it below the horizontal. So inverse tan of 0.396778 divided by 15.45486 is not very big, which is not surprising because we've got a teeny tiny y component and a fairly large x component. So that's about 1.5 degrees. And normally I would tell you to round angles to the nearest whole number. And that would be okay to do here. We could call this 2 degrees. And then in terms of direction, if I don't give you compass directions in a problem, instead of writing it in terms of compass directions, like south of east, you can write below the horizontal. Which is a better way to describe a direction in the case where you don't have compass directions. So the net force is 15 newtons at an angle of 2 degrees below the horizontal. And of course, in momentum, this comes up when we're doing two-dimensional conservation of momentum. You're going to be finding the total momentum in the x direction and the total momentum in the y direction, and then putting those values back together again. When we go into electrostatics, which is module 3, you're going to be combining forces on a particle. So for example, this is something where this might come up. Let's say you have an electron, which is a negative charge. And then you have perhaps an electron here and another electron here. And let's keep it another electron here. Then electrons are repelled from other electrons. We know that negatives repel other negatives. So this electron, the first one I drew, is going to have a repulsive force from this electron. Let's call this F2. And it's going to have a repulsive force from this electron. Let's call this F1. And it's going to have a repulsive force from this electron. And I'll call this F3. And so this picture that I've just drawn looks an awful lot like this picture that I drew at the beginning of this example. And so by the exact same method, if I know the force on my electron, or I know each of these 3 forces on my electron, I could find the net force on the electron by adding up F1, F2, and F3 like vectors. So that's where we're going with module 3 in the coming weeks.